In this section, we'll be looking at implicit differentiation in the Achieve 3.8. They start off by telling us a function is with respect to t, and that x is a variable that is in terms of t as well. So we're supposed to differentiate t cubed x to the seventh with respect to t, assuming that x is implicitly a function of t. We just don't know what it's equal to in terms of t. So whenever we take the derivative of x, we can't simply just call it 0. It's not a constant with respect to t. So normally I would call it dx dt. But in this problem, they're asking me to call x prime instead of dx dt. I think dx dt is far better notation, but we'll go ahead and stick with what they want in this problem. So when I take the derivative with respect to t in this problem, I can say, well, all right, it's a product. It's the function t cubed times the function x to the seventh. And again, since x is a function of t, so now when I take the derivative, I say, well, the derivative of the first, 3t squared, times the second, plus the first, t cubed, times the derivative of the second. And here's where I have to say 7 times x to the sixth. And this is really where you're thinking chain rule, because you can say, well, x is some group of a function of t. We don't know what it is. So whenever we take the power rule on the outside, the 7x to the sixth, then we have to say, ooh, times the derivative of what's on the inside. We don't know what the derivative of the inside is. So we represent that by x prime, whatever the derivative of x is with respect to t. That would be my final answer for this first one in the format that they like. And you can see I typed it in to achieve the exact way I have here, and it was fine. When I go to the second problem here, there's really nothing to this one. I don't like it. In this section, we're also looking at our inverse trig functions. They're just wanting you to know that if g prime of x is equal to 1 over x squared plus 1, well, it's because the original function had to be the inverse tangent function. The only way you could possibly know this is if you have your derivative formulas from this section memorized, where you say, well, the derivative of the inverse tangent of x is 1 over x squared plus 1. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. The derivative of the secant of x is 1 over the absolute value of x on the square root of x squared minus 1. So you do need to have those memorized at some point. This one, so this problem is just working backwards and understanding that if this is the derivative, then the original problem had to be the inverse tangent function. Number 3 gets a little more interesting, hopefully. Yeah, sorta. Still not a fun problem. We have the derivative with respect to x, and now this time it tells us in the problem that t is implicitly defined as a function of x. So t could be x to the fifth. T could be the secant of x cubed. We don't know. But what we do know is that its derivative is not simply 0. Whenever we take the derivative of t in this problem, they're telling us to use t prime. Again, a far better notation for the derivative of t with respect to x would be dt dx, but they're asking us to use t prime, so we will. So when I look at this function, first of all, I need to understand that the x and the t are inside the angle of the tangent function. So when I first take the derivative with respect to x, I can say, well, it's the derivative of the outside. Derivative of tangent is secant squared. I keep the angle. Now I multiply by the derivative of that angle. And when I do that, it's the product rule. So I say, well, the derivative of x to the fifth is 5x to the fourth times the second, plus the first, x to the fifth, times the derivative of the second. Well, the derivative of t with respect to x is just t prime. We don't know what it is. We just have to put it t prime in the problem. So now this would be my first derivative with respect to x of this problem. I entered it into Achieve just this way right here. And for the prime notation, I used the apostrophe button on the quotes button, and it worked just fine. For number 4, a little bit better because at least we have a quotient in there. And now you can say, well, in this problem, y is specifically defined as a function of x, and it's telling us to state its derivative as y prime. Okay, so when I go in and I look at this, I can say, okay, the derivative of y is not 0 because y is a function of x. So when I take its derivative, quotient rule says square the denominator. Bring the denominator up to the numerator times the derivative of the numerator. All I can do is y prime minus the numerator, y, times the derivative of the denominator. And again, it's just going to be y prime, and derivative of 5, of course, is 0. So when I'm looking at what I have here, I know I'm going to have y times y prime minus y times y prime. Those cancel. And so my only term in the numerator that remains is 5 times the derivative of y all over y plus 5 quantity squared. And you can see that's what I entered in to achieve in this problem, and Achieve liked it. For the next question here, number 5, it finally starts getting into the problems that I more so like. I'm not crazy about those first 4 problems. Number 5 and on, pretty cool stuff. So in this one, it no longer keeps on telling you use the prime notation, which honestly I think is sloppy. It's asking us to find the derivative of y with respect to x. So I look at my original relation here and I say, okay, I'm taking the derivative with respect to x, but I need to remember y is a function of x. So when I take the derivative of the first term, I'm thinking chain rule. 3 comes down in front, times the group to the second, times the derivative of the inside. Well, the derivative of y with respect to x is dy dx. So all of this is the derivative of the first term. Now I go to the second term. Derivative of x squared is 2x. Technically, if you tried to say, well, times the derivative of the inside, it'd just be the derivative of x with respect to x, which is just multiplying by a 1. So I can say, okay, done with the derivative of the left, derivative of the right, it's a constant. Its derivative is 0. Now I need to isolate dy dx by moving the 2x over. It becomes a negative 2x, dividing by the coefficient of dy dx. And you can see I have negative 2x over 18y to the second. That's going to simplify to give me negative x over 9y squared. And that's the answer I put in Achieve. And it was fine. For the next one, a better problem, getting better. Woohoo! I have a more complicated looking relation, and I'm asked for dy dx. Okay, so I start taking the derivative term by term. In this first term, I need to understand product rule. So the derivative of 8x squared, 16x, times the second, plus the first, 8x squared, times the derivative of the second. Well, the derivative of y with respect to x is dy dx, plus derivative of this term, again, product rule. Derivative of the first is going to give you 15x to the second times the second, plus the first, 5x cubed, times the derivative of the second. Yet again, that's going to be a dy dx. Now, on the right-hand side, the derivative of 5x is just 5, and the derivative of y with respect to x is dy dx. Now, I knew I was trying to solve for dy dx, so I would put this term, and this term all on the left, every other term on the right. Since I'm going to move the terms that have a dy dx to the left, might as well go ahead and factor it out. So I can say, well, the dy dx terms had an 8x squared plus 5x cubed, and then when this one comes over, it'd be a minus dy dx. When you factor it out, it's left with a minus 1. So all of these 3 terms were my factors of dy dx. My other side, 5, and then I move over the 16xy, it becomes minus 16xy. I move over the 15x squared y, it becomes minus 15x squared y. So now I have dy dx times this group is equal to this group, thus dy dx is equal to what I had on the right, divided by 8x squared plus 5x cubed minus 1. Final answer, nice problem. I really like that one. you can expect to see a problem like number 6 in the future, for sure. Number 7. It says r is a function of x, and we're supposed to find dr dx. Okay. Other than the unusual choice for variable, it's pretty easy. You just say, well, the left-hand side's derivative is going to be taken with the product rule. Derivative of the first, 3x squared, times the second, plus the first, now times the derivative of the second. Derivative of r to the fifth is 5r to the fourth, times whatever the derivative of r with respect to x is. And you need to understand this is just a result of the chain rule. The derivative of the inside with respect to x is dr dx. Now, some people might think, well, why didn't you have to do that over here? Because the inside was an x, and the only thing you could possibly put after it would be dx dx, which is pointless because that's just a factor of 1. Now, on the right-hand side, derivative of any constant, 0. Now I come down, I need to solve for dr dx. So I can say, well, the 3x squared r to the fifth is going to move to the right and become negative. It then is divided by all of these terms that are multiplying dr dx. So you'll see I have negative 3x squared r to the fifth divided by 5x cubed r to the fourth. And then I just reduced that down. It reduced down to negative 3 over 5, and then you had 1 power of r left in the numerator, 1 power of x left in the denominator, and you'll see that's precisely what I entered in, negative 3r over 5x, excellent. For number 8, we had 6y over x plus x over y is equal to 3y. The first thing you can see I didn't want to do 2 quotient rules to take the derivative of that left-hand side. I moved the denominators up, put them to a negative exponent, so I called it 6y x to the negative 1 plus x y to the negative 1 is equal to 3y. I feel that's much easier to take the derivative. Now, product rule here. Derivative of the first, 6 dy dx, times the second, plus the first, 6y, now times the derivative of the second. That's going to give me the negative 1x to the negative 2. So all of this is the derivative of that first term. Now I go into this term and say, okay, yet again, product rule. Derivative of the first is 1 times the second, plus the first x, now times the derivative of the second. Derivative of y to the negative 1 is going to be negative 1 times y to the negative 2. Now, I need you to make sure you understand the difference in why the derivative of x to the negative 1 was just negative 1x to the negative 2, but the derivative of y to the negative 1 is negative 1y to the negative 2 times the derivative of the inside, which is dy dx. Here, if you said times the derivative of the inside, it would be dx dx, which is just a factor of 1. So this is not a different rule for derivatives of y versus derivatives of x. It's just if you tried to do the chain rule derivative here, you'd just be multiplying by a factor of 1. You're not here. The derivative of the inside with respect to x is dy dx. Now, on the right-hand side, 3 times the derivative of y, well, that's 3 dy dx. And I ran out of room, so I had to write it up there. Now, I need to simplify. So just like the problem above it, I said I need to get all of the dy dx terms on the same side. So I have 1, 2, 3 terms with a dy dx. I factor the dy dx out. My first term, 6x to the negative 1, that's better written as 6 over x now, since we don't need to take the derivative anymore. My next term that had a dy dx is this term. If I factor that dy dx out, it's going to become minus that negative minus x over y squared. That's where that came from. And then, of course, this 3 dy dx, if I move it to the left, it's a minus 3 dy dx. Factor out the dy dx, you're left with a minus 3. Now, what do I have on the right-hand side? Well, this moved over, so it's no longer on the right. This term belongs on the right. It was positive on the left, so it's going to be negative on the right. So I would say, well, that's going to be 6 over x there. Oh, I'm sorry. That term had a dy dx. That's that term. Ooh, John. This term doesn't have a dy dx, so it needs to be moved to the right-hand side. It would be negative 6y over x squared on the left. That's why it is positive 6y over x squared on the right. This term also did not have a dy dx, so it needs to be moved to the right. On the left-hand side, it was positive 1 over y. On the right, it becomes minus 1 over y. Now, this is my gorgeous next step, and I can say, well, if dy dx times this is equal to the right-hand side, then dy dx is equal to what I had on the right divided by what dy dx was factored out of and multiplying. And then I just wanted to make it look nicer. You could have entered this answer, and I'm sure Achieve would have accepted it. But I just don't like the compound fractions, the fractions within the fraction. So I multiplied by the least common denominator of all the fractions in there. I multiplied by x squared and y squared in both the denominator and the numerator. When I did that in the numerator, you're going to have 6y to the third, and then minus, you would have x squared y for the second term. If you distribute that to the 3 terms in the denominator, you're going to have 6xy squared. And then you would have minus x cubed, and then the y would cancel out, and then you'll have minus 3x squared y squared. And I just think that looks like such a much better answer. But again, you probably could have entered the previous answer and Achieve would have been fine with it. But better answer, always a good thing to have. Now, next page here, at least of my work, I started working on number 9, where it asked me to find the implicit derivative for y to the negative 3/5 plus x to the 5/3 is equal to 1. Well, my work in that problem is as follows. So I said, all right, if this is my original function here, y to the negative 3/5 plus x to the 5/3 is equal to 1, take the derivative of the first term. Well, the chain rule says the negative 3/5 comes down in front times y to the negative 8/5, subtract 1 from the exponent. Then it would say times the derivative of what's inside the group. And please remember, that y is really a group. It's some function of x. We just don't know what it is. So you say, well, it's the derivative of whatever that inside is. That's dy dx. Now, plus derivative of x to the 5/3, that's just 5/3 x to the 2/3. And if you put anything after it, it'd have to be dx dx. So it's better not to put that because that's just a factor of 1. Move to the right-hand side, derivative of any constant, 0. So now I need to simplify. I need to get the dy dx term by itself. So I just said, okay, if I try to get that term by itself, I noticed, first of all, if I moved the 5/3 x to the 2/3 to the right, yes, it would be negative. But then I would be dividing by a negative. So I just went ahead and said a negative over a negative is a positive. I'll have 5x to the 2/3 divided by 3/5 y to the negative 8/5. And then I didn't really think that looked very nice, so I cleaned it up. I know that 5/3 divided by 3/5, anytime you divide by a fraction, you multiply by its reciprocal. So this is 5 over 3 times 5 over 3, which gives me 25 over 9. Then I had x to the 2/3, and y in the denominator to a negative exponent means y belongs up in the numerator to the positive 8/5 exponent. And that's the way I entered my answer in on Achieve, and Achieve liked it. For number 10, I think I'll go ahead and just maximize this so I can show my work a little better. For number 10 here, we have x to the 1/2 plus y to the 5/6 is equal to a negative 6y. Okay, so the derivative. And again, we're finding dy dx, so I can say since I'm taking the derivative with respect to x, that x to the 1/2 just becomes 1/2 x to the negative 1/2. But now the y to the 5/6, more tricky. I have to worry about the derivative of the inside. So I'll have 5 over 6 times y to the 1 lower power, negative 1/6, times the derivative of y, which is dy dx. Now, on the right-hand side, the derivative of negative 6y becomes negative 6 dy dx. I want to get the two dy dx terms on the left-hand side. I go ahead and factor it out. My first term is going to be 5/6 y to the negative 1/6. This term, when it moves over, is going to give me a plus 6. Now, the term that didn't have a dy dx right here moves to the right-hand side. It's going to become a negative 1/2 x to the negative 1/2. So my final answer, dy dx, equals what I had on the right divided by the expression it was factored out of. And that's a good answer at that point. Looks a little sloppy with the negative exponents in there, but really not a nice way to get rid of it since it's not a factor in the denominator. So I would just leave my answer like that. And I assure you, that's how I entered it in on Achieve, and Achieve liked it. For number 11, gives us a trigonometric expression with these relations of x and y. So we have the sine of x plus y is equal to 3x plus 3 cosine y. Okay, derivative of the left-hand side. Derivative of sine is cosine. I keep the angle. Multiply by the derivative of the angle. Derivative of x is 1. Derivative of y, dy dx. Now, that's going to equal the derivative of the right-hand side. Derivative of 3x is 3. The derivative of 3 cosine y is going to be minus 3 sine of y times the derivative of that angle, derivative of y, dy dx. Now, at this point, and here's a lot of students struggle with this because they fail to see that there's really two terms on that left-hand side. The cosine of the angle x plus y is multiplying 1, and it's multiplying dy dx. So when I say I want to get all dy dx terms on a side by itself, I can say, well, the dy dx is multiplying this term. So dy dx, I'll have cosine x plus y. And then it's also multiplying this term. If I move that to the left, it's going to become plus 3 sine of y. Now, I need to make sure you see where I'm getting the rest of this from. Well, the 3 was already over on the right, but I need to move any other term that doesn't have a dy dx to the right as well. And you need to understand that there's another cosine of x plus y term that is not multiplying the dy dx on the left. So you say, then that cosine of x plus y needs to move to the right-hand side. And when it does, it becomes a minus cosine of x plus y. So now dy dx is equal to what I had on the right, divided by cosine of x plus y plus 3 sine y. Final glorious answer there. I like that problem. I like it, I like it, I like it. You can expect to see one like number 11. For number 12 here, throwing some exponentials in there. But remember, exponentials, they're easy to integrate. Sorry, to differentiate. Well, they're easy to integrate too, but they're easy to differentiate. We just say the derivative of any exponential function is that exponential function times the derivative of its exponent. So when I look at this one, I can say, all right, the left-hand side, it's the differentiable function x times the differentiable function e to the y. So I'm thinking product rule. Derivative of the first, 1, times the second, plus the first, x, now times the derivative of the second. Well, derivative of e to the y is e to the y times the derivative of its exponent, dy dx. I move to the right-hand side. Yet again, product rule. Derivative of the first is 2 times the second, plus the first, 2x, times the derivative of the second, dy dx, plus the derivative of y to the fifth. And so, well, that 5 is going to come down, and I'll get y to the fourth times the derivative of what's inside, dy dx. And I had to kind of scrunch that in there. Now, on the left-hand side, I want to get every single dy dx term over there. So I go ahead and I factor a dy dx out. I'll have x e to the y. When I move this term over, it'll become minus 2x. When I move this term over, it'll be minus 5y to the fourth. Every other term that doesn't have a dy dx needs to be on the right. I already had a 2y over there. And that this e to the y becomes a minus e to the y on the right. So now I can say that 2y minus e to the y needs to be divided by everything that was multiplying dy dx, and that's your final answer. Glorious. For number 13 here, you have the exponential function e to the 2xy is equal to the sine of the angle y cubed. All right, derivative of that left-hand side. Derivative of any exponential function is that exponential function times the derivative of its exponent. Now, the derivative of its exponent, I have to be careful. It's a product. So I can say, well, the derivative of 2x is 2 times the second plus 2x times the derivative of the second. And we know derivative of y with respect to x is just written as dy dx. Now, all of this is the derivative of the left-hand side. I move to the right, and it's going to be a chain rule again. You have a differentiable function inside of a differentiable function. Derivative of the outside is cosine. I keep the angle y cubed. Now, times the derivative of that angle. I can say, well, the derivative of y cubed is going to be 3y squared times the derivative of what's inside of that group. And you say, well, that's your dy dx. If this was an x there, I would have been done at this step. But since it's a y, and I don't know what the derivative of y is here, that's what I'm trying to solve, I have to account for that and put a dy dx. Now, every term that has a dy dx needs to stay on the left-hand side. So I see I have all of this is one big factor with a dy dx. I have another one right here. And then I have this term right there that does not have a dy dx. So I can say, okay, dy dx gets factored out, and I'm going to have 2x e to the 2x plus y. That's where all that came from. And then when I move this term over, it's going to be minus 3y squared cosine of y cubed. Again, I factored out the dy dx. Now, is equal to, and it's extremely important that you see where this comes from. If I would have distributed on that left-hand side, I didn't want to do yet another step and show that, you'd see that you had two terms on the left. The second term had the dy dx, the first term did not. It would just be a 2y e to the 2xy. When you move that to the right-hand side, it becomes a minus 2y e to the 2xy. All right, so now I can say dy dx is equal to that group on the right divided by what dy dx is factored out of for our final fantastic format of the answer. And there's really nothing you can do to simplify that answer either. So it's already in glorious final form. 14 is just getting into our inverse trig functions. And this is just a matter of you have to have those inverse trig derivative formulas memorized. Inverse tangent of x, 1 over 1 plus x squared. Inverse sine of x has a derivative of 1 over the square root of 1 minus x squared. Inverse secant of x has the derivative of 1 over the absolute value of x on the square root of x squared minus 1. And if it's the inverse cosine, it's just the negative of the inverse sine's derivative. If it's the inverse cosecant, it's just the negative of the inverse secant's derivative. If it's the inverse cotangent, it's just negative 1 over 1 plus x squared. It's the negative of the inverse tangent's derivative. So you really only have to memorize three: the inverse sine, the inverse tangent, and the inverse secant. And then remember, anything with a co, it's just the negative of the other version. Now, so when I say, all right, I have to know derivative of the inverse sine of x is 1 over the square root of 1 minus x squared, I do know that. So the derivative of 5 times that is just 5 times this group. Now, on Achieve, it wanted me to evaluate this derivative at negative 3/4. Okay, I plug in a negative 3 over 4 in the place of x after I've taken the derivative. And I know that negative 3 over 4 squared, that's going to be a positive 9 over 16. But remember, it's still being subtracted. That's why I have 5 over the square root of 1 minus 9/16. So in my head, I just thought, well, that's 16 over 16 minus 9 over 16, which gives me the root of 7 over 16. And then I was thinking, well, if you're dividing by a fraction, you're multiplying by its reciprocal. So I multiplied by the root of 16 over the root of 7, and then we know the root of 16 is 4. And so this just gave me 20 over 7, and it wanted me to leave the answer exact. No reason on earth that you should rationalize that. In fact, rationalizing it, in my opinion, gives an inferior answer. You can see achieved like the answer just like that. Okay, now I'll stop at this point so this video won't get too long and Zoom knocks me off. I'll do the remainder of the problems 15 through 24 in a second video.